Okay, so in the last class, we were looking at the proposition logic, and we talked about certain laws that are possible through proposition logic. Uh, Today, I am going to introduce what is known as predicate logic, the second type of logic, and then briefly we will talk about the Boolean algebra, and then in the next class we will talk about rules of inference and certain normal laws. So basically, let me start with the predicate logic. Okay, so as you know, in the propositional logic, we have certain statements and they're either true or false, right? But in actual practice in computer science or in the normal languages, in English language, say for example, there are cases when there are variables associated with the statements. So in that case, it will be very difficult to say whether that variable statement is true or false. So for example, if I write down, I'll take an example first. P of x is statement says that x is greater than 3. So now this is may be possible that this statement is true or false for different values of x, right? For example, we know that P of 4 is true, right? Because 4 is greater than 3, and P of 2 is false because 2 is less than 3, it is not greater than 3, right? So these kind of scenarios may occur in mathematics, computer science, and in actual languages. So in general, there may be n variables rather than single variable, right? So we have x1, x2, xn. Okay, so this is the value of the proposition function p. Okay, at the n tuple, x1, x2, xn, and p is called, so I would say that p is also called n place predicate, right? Or n-ry predicate. Okay, so this is a definition of predicate logic, right? So which could be true or false for different values. So now, in fact, there are certain objects known as quantifiers. Quantifiers. What are quantifiers? So quantifiers expresses the extent to which a predicate is true over a range of elements, For example, in case of some mathematical statements, it might be possible that x range over a real numbers and so on, right? So quantifiers, so these things are known as quantifiers. So they expresses the extent to which a predicate is true or over a range of elements. So there are some specific kind of quantifiers which I would like to mention now, known as universal quantifiers. So what are these universal quantifiers? Okay. So I can write it down. So universal quantification of Px, suppose Px is our variable statement. So is the statement that Px for all values of x in the domain. Okay. So this is the universal quantifier. So notation for this is for every x, Px. So for every is nothing but a universal quantifier. Okay. For every is a universal quantifier. And sometime it may happen for some value of x or maybe a single value of x, Px is false. Okay. So if that happens, so if Px is false for some x, so we say that x is known as counter example. So it may be true for all, but except for few, or maybe, so counter example of for every x, Px. Okay. So I can make a table for you here. Is a statement when true, when false. Okay. Statement is for every x, Px. Okay. So Px, so when true means Px is true for every x. Okay. When false, there exists an x for which Px is false. Right? And if the statement is there exists x, Px, so it is true. When it is true, there is an x for which Px is true. Okay. And when it is false, we say that Px is false for every x. So this is a summary for you. Okay. So for every x, Px is true for every x. When false, there exists an x for which Px is false. And if the statement is there exists x, Px, when it is true, there is an x for which Px is true, right? And when false, Px is false for every x. Okay. Now again, I would like to give you some examples before proceeding.
Sir,
Yes.
sir, in the last statement of that exists x p of x, it is not false at every x, right? Px is not false at every x.
You mean to say this is statement?
No, the statement below it.
Yeah. So Px is false for every x actually,
But
because the statement is there exists x only, right?
but that exists x for which Px is true, no, sir.
Uh-huh. No, so
it
when it is
cannot be.
when so we are saying when it is false, it's not happening at the same time, both the things, right? Okay. So I'm saying that when this will be false, okay, the whole statement there exists x px is false when we so this is false for every x.
Oh
Okay.
yes, yes, yes.
Okay.
Understood, understood. Okay,
Yeah.
yes.
Yeah.
It
Yeah.
was other way around. Yes,
Yeah.
yes.
Yes. Yes. Yes. Okay. So let me give you some examples now. So many times people say that do we really need to understand logic? So there are different order of logic, right? So sometimes there are confusions as well, right? Which is okay. Okay, so the first example that I would like to give, px is x plus 1 greater than x. Okay, so what is the truth value of the quantification for every x px? So if I ask for every x px, what is the truth value?
So it is a tautology.
Yes,
Yes, sir, total logic.
good, good. Truth value. Okay, so we know that I mean we can assume that of course domain is real numbers, right? So since px is true for every x in R, we know that this is a straightforward statement. So the quantification for every x px is true, right? Good. Second example, let us take px x is greater than 3. So what is the truth value of the quantification? There exists x px. This time quantification is this. There exists x px. Domain we can assume the same, real numbers. Okay. So what is the truth value of this? What is the truth value? I can write it down. Okay. So for this quantification, since on the real numbers x is greater than 3 is true sometime, right? Not always, right? Sometime, say when x is equal to 4, right? So therefore, there exists x px is true, right? So there exists x for which it is true. Fine. So these are two examples. There are other quantifiers which are important. In fact, I am just mentioning them. Other quantifiers. So one of them is there exist unique x px. This stands for unique, okay? Or so I think yeah, this is how you write. So that means there. I should write it on in English also. There exists a unique x. You might have noticed while writing the proofs, etc. I have used the symbols many times. Unique x such that px is true. Okay, so this is another quantifier. Okay, so now just like that in the proposition logic we have precedence of operators. Here also we have the precedence of these quantifiers. So I would like to mention what are these precedents. Precedence of quantifiers. Okay, so for every and there exist have higher precedence. Then all logical operations. So for example, for every x px disjunction qx is disjunction of we call it join also, right? Of for every x px and qx. Okay. Okay, so this is not so basically what does this mean? Basically we have first you need to compute this, then qx, and then you do this join. So this does not mean that we are doing it like this. We cannot do like this. For every x px qx. So we should not combine these two first and then for every, right? Because this has higher precedence. So for every x should be executed first and then qx, and then we have any other logical operations. Okay, so I hope this is clear to you. Okay, so precedence of quantifiers. So just
Sir,
yeah,
sir, instead of and there will be or no, for every x px or qx.
and कहाँ लिखा है मैंने?
अब डिसजंक्शन के बाजू में.
Yeah, I mean, oh, here you mean to say?
Yes, yes, sir.
Oh, okay. I mean, I just wanted to maybe I should not write anything, otherwise there will be confusion actually. Anyway, okay.
Okay.
Definition for these two quantities. So basically, what I'm saying that we are actually for every has to be executed first, rather than this logical operation, right? Okay. Okay. So now, so we have done with the precedence of quantifiers. Next important thing is just like that in the proposition logic, we have logical equivalences. So we can talk about those things here also in terms of quantifiers, involving quantifiers. Involving quantifiers. Okay, so logical equivalences involving quantifiers. What are these things? So statements involving predicates and quantifiers are logically equivalent if and only if, I would say that statements involving predicates and quantifiers are logically equivalent if and only if they have the same truth value no matter which predicates are substituted into the statements and which domain of disclosure is used. Okay, so no matter I should write down this thing because it's important thing. No matter which predicates are substituted into these statements and which domain of disclosure is used, which domain is used, right? For the variables okay, so we write it like s is equivalent to t, something like that. So let us again see an example. Okay, maybe in the next slide let us look at an example of logical equivalence involving predicates and quantifiers. We want to show that for every x px be it qx is logically equivalent to for every x px and for every x qx. So it involves quantifiers and predicates both. So let us see a small proof of this fact. So what we can do, suppose left hand side, which is for every x, px meet qx. Just check, because I do many times mistakes. In the last class I have done a mistake while writing, so just stop me if I am writing anything wrong. For every x, px meet qx, okay, is true. Suppose this is true, okay. This implies that if a is in the domain, okay, we will have, because this is true for every x, this will be true for a also. We will have pa meet qa is true. This implies that pa is true and qa is true, and this is true for every a in D, right? Because we have taken a to be an arbitrary element. Now that means for every x, px and for every x, qx are both true. Both are true actually, right? This implies that for every x, px meet for every x, qx is true. Okay. So one side is done. So we started with left hand side. We arrived at the right hand side. So we can do the opposite, and suppose for every x, px meet for every x, qx is true. This implies that for every x, px is true, and for every x, qx is true, right? Hence, if a is an element in the domain, then pa is true and qa is true, right? Because px and qx are true for every x in D. Since px and qx is true, I mean they are true, I mean they both are true for every x, right? They both are true. This implies that for every a in D, from here we have pa meet qa is true. This implies that for every x, px meet qx is true. And this is a nice, small, beautiful proof logical equivalence of these two statements. So I think in the book you will see that many such logical statements are given involving quantifiers and predicates. So I invite you at your tea time, try to prove them like this, okay, systematically. So here actually very important, wherever you have to write for every, you will write for every. Wherever you have to write, anything else like there exists, so it should be there exist. So preciseness is very, very important. Otherwise things will become wrong actually. Okay, fine. Now we go to define what is known as negation of the quantified expressions, negating quantified expressions. Okay, so we talk about this. Okay, so first I'll take an example. For every x, px is that every student in your class has taken a course in calculus. I think last semester you have done that actually, right? So every student in your class has taken a course in calculus, right? So negation of this will be, so we say that negation of for every x px, it is not true. So it is not the case that every student in your class has taken a course in calculus. This is the negation, right? So that means, I mean, this is equivalent to saying that there is a student in your class who has not taken a course in calculus, right? Same thing. So the statement saying that it is not the case that every student in your class has taken a course in calculus, equivalent of saying that there is a student in your class who has not taken course in the calculus. This implies that equivalently we can say that there exists x such that negation of px happens, right? Right. So thus we arrive at the following logical equivalence: negation of for every x px is logically equivalent to there exists x such that negation of px. Okay, so this is a simple observation of negating the quantifier. Okay, so I guess again I can make a table. So last time I think, yeah, I think while teaching the Demagogues Law, because I wrote it wrong there, in the join and meet while writing. So I think we were doing the Demagogues Law last time, but I think while writing, so I said that we are not doing Demagogues Law. But anyway, so now we can talk about Demagogues Law for quantifiers. Okay. So what are the Demagogues Law for quantifiers? Okay, so since we have the negation now with us, so negation, then we can talk about equivalent statement. Then we can talk when is negation true and when false. So we can make a table here, small nice table. Negation of there exists x px, equivalent statement will be for every x negation of px, right? So what is negation? When is negation true? For every x px is false, right? And when false, there is an x for which px is true, right? Similarly, the other part, negation of for every x px, equivalent is there exists x such that negation of px, equivalent statement. When the negation is true, there is an x for which px is false, and when it is false, px is true, for every x. Okay, so these are the what is happening, I think. Please mute your mic, Okay, so I think now I am going to talk about nested quantifiers. This is also an interesting thing. So, nested quantifiers. What are these nested quantifiers? So basically, it involves more variables. So for every x, qx, okay, where qx is there exists y pxy, where pxy is x plus y is equal to 0. So this is an example of nested quantifier, right? So where for every x qx, where qx is there exists y such that pxy, where pxy is x plus y is equal to 0. So I think if I give an example, so you can see that if we take domain to be the real numbers, then for every x there exists y such that x plus y is equal to 0. So for that means for every real number x there is a real number y. Such that x plus y is equal to 0. Okay, so in fact we can again make a table for quantification of two variables. So let me do it for you. And after that I will give one example of two variables. So a statement, then we have when it is true and when false. So statement is for every x, for every y, pxy. Okay, so when it is true, pxy is true for every pair x comma y, and when false there is a pair x comma y for which pxy is false. Okay, same thing is true for every y, for every x, pxy, so I'm writing it here just like that. If we have the statement like for every x there exists y pxy, that means for every x there is a y for which pxy is true. So for every x there is a y for which pxy is true. Okay, and false there is an x such that pxy is false for every y. Okay, so that is when it is false. Similarly, we have there exists x for every y pxy. That means there is an x for which pxy is true for every y. Okay, there is an x for which pxy is true for every y when it is true. When it is false, that means for every x there is a y for which pxy is false. Okay, finally we have the last set of statements. There exists x, there exists y, pxy, or we could be having there exists y, there exists x, they are symmetry, x comma y. That means there is a pair x comma y for which pxy is true, correct? Which is very obvious. And when it is false, pxy is false for every pair x comma y. Okay, so in that case it is false for every pair. So this is a quantification for two variables or possibilities I have written, and when they are true, when they are false. Now I am going to give you one example, in fact, and that is an important example, and then we can finish this section of predicate logic. Qxy is a two variable statement, is x plus y is equal to 0. So we can ask the question, what are the truth values of the quantifications there exist y for every x qxy, and another question actually, for every x there exists y qxy. These two statements are there, I mean these two quantifications are there, where of course the domain is x comma y belongs to real numbers. So we need to check their truth values. First, we will check the first one. There exists y for every x qxy. Okay, so that means there is a real number y such that for every real number x qxy. So no matter what y is chosen, because there exists y, right? No matter what y is chosen, there is only one value of x such that x plus y is equal to 0. Since there is no real number y such that x plus y is equal to 0 for every real number x, this statement is false. The statement there exists y for every x qxy is false, right? Because there is no real number y such that x plus y is 0 for every real number x. Okay, so this is false. The second one is for every x there exists y qxy. Now in this case, for every real number x, for every real number x, because for every x, right, there is a real number y such that x plus y is equal to 0. Why? Because since y will be minus x for every x in R, right? This implies that our statement for every x there exists y, qxy is true. So one statement is false and one statement is true with respect to these quantifications, you know. So I think that's all for predicate logic. So what we covered, I will quickly recover. I'll give you a summary. So we talked about predicate logic, basic definition, quantifiers, universal quantifiers, their truth values, precedence of quantifiers. We talked about logical equivalence of involving quantifiers. Then I gave you an example. So in the book you will find tables of such things, and I think you can verify each of them in your tea time. So then negation of the quantified expressions, Demagogues laws with respect to this, nested quantifiers we talked about, and their truth values, and finally one example I gave. Okay, so I think that's all for predicate logic. Now I am going to tell you something about Boolean algebra. In the next class, I am going to talk about rules of reference, actually for proposition logic, and we'll also talk about the normalization laws. You know, so we'll talk about Boolean algebra given by George Boole. That's why it is known as Boolean algebra. Your set B is 0 and 1 binary set. We denote 0 bar by 1, 1 bar by 0. So I think most of you are doing also course in electronics, right? Or you digital logic you have done already, right? Anyone can answer?
No, sir, it is going on.
Okay. So there you will see most of these stuff, you know. Anyway, we can talk about Boolean sum, which is or we call it as or. So 1 plus 1 is 1. 1 plus 0 is 0. Sorry, 1 plus 0 is 1. 1. 0 plus 1 is 1. 0 plus 0 is 0. This is the plus sign or this or this, right, is always this. Similarly, there is a Boolean product which or we also call it this or and, we denote it by and, right? So this is 1 into 1 is 1, 1 into 0 is 0, 0 into 1 is 0, and 0 minus 0 is equal to 0. Okay, so example, I can give you again an example of this Boolean algebra. 1 into 0 plus 0 plus 1 complement. Complement, we know 0 complement is 1, 1 complement is 0. So this will be 1 into 0 is 0, 0 plus 1 is 1, complement, which is 0 plus 0 is equal to 0. So this is how you can simplify the expressions, right? These are the basic rules. Using these basic rules and this complement rule, we can find out, we can do the calculations. So we can talk about Boolean functions or Boolean expressions and Boolean functions. So if b is equal to 0 comma 1, bn will be set of all n tuples like x1, x2, xn such that xi belongs to b, 1 less than or equal to I less than or equal to n, right? It's cross product kind of thing, you know, b cross b n times. So a variable, you know, so this is the whole space actually, Boolean space. So we can define what is known as, Boolean function and variable. So a variable x is called Boolean variable if it assumes values only from B, only from set B. So there are only two values, 0 or 1, right? Okay. And a function from Bn to B. So n inputs and one output is called a Boolean function. By the way, these Boolean functions are quite useful in ciphers, cryptography, and security. And there you will find many of books involving Boolean functions. Their characterizations, they're also useful in communications. So very useful object, the Boolean functions. Okay. So example I'm giving you again, another example of them. fxy is equal to xy. So it's a Boolean function of degree 2. So this is defined for every x comma y in B square. And so basically Boolean expressions in variables x1, x2, xn are defined recursively as first 0, 1, x1, x2, xn are Boolean expressions. Second, if E1 and E2 are Boolean expressions, this implies that E1 complement, E1, E2 and the product E1 plus E2 are Boolean expressions, So let me give an example here now. Find the values of the Boolean function fxyz xy plus z complement, right? So what I can do, I can make a table x, y, z, then another component is xy, then z. Of course, z complement can be done. And finally, xy comma z, which is xy plus z bar. Okay, so when x is 1, y is 1, z is 1, of course this product will be 1, and we can assume z is 0. Okay, then this value is 1. When this is 1, this is 1, this is 0, this is 1, this is 1, then this is 1. 1, 0, 1. I'm just filling. Actually, you can verify if I'm making any mistake. It's 0, 1, 0, 0, 0, 1, 1, and 0, 1, 1, 0, 0, 0, 0, 1, 0, 0, 1, 1, 0, 0, 1, 0, 0, 0, and finally 0, 0, 0, 0, 1, 1. So you can see that there are 3 variables x, y, and z, and we have varied them. 2 choices for each of them, so there are total 8 possibilities, right? By varying all the 8 possibilities, we got the values of this function here, Boolean function. Okay. So I think Boolean functions, so these are very useful in the discrete sense, basically, So Boolean functions can be represented by a n cube, n tuples of bits, where the function has value 1, right? So these, 3 inputs and 1 output, 3 input, 1 output, 3 input, 1 output, right? Okay. Now we can define the complement of Boolean function f as a function f complement, right? So essentially f complement x1, x2, xn, same thing as f of x1, x2, xn whole complement. Okay. Similarly, we can define a Boolean sum of expressions, f plus g. So it is f plus g x1, x2, xn is equal to f of x1, xn plus g of x1, xn. Okay. One can ask a question: how many Boolean functions are there of degree 2? How many Boolean functions of degree n are there? Right. So functions are, remember, from b raised to power n to b. Okay. So since cardinality of b raised to power n will be 2 raised to power n, each of these n tuples assigned to 0 and 1, right? So that means there are 2 raised to power 2 raised to power n Boolean functions of degree n. Okay. Now I think I will show you some laws rather than proving them. Okay. And let me show you this. Yes. So now you can see that these are the nodes which I am actually covering. So there are identities of Boolean algebra. So x times y plus z is equal to xy plus xz. And how do we verify? We can actually see that I write down x, y, z, y plus z, x, y, x, z, x times y plus z, and x, y plus x, z, right? So this is the left hand side and this is the right hand side. You can see that for each values of x, y, z, there are total 8 possibilities. I can compute everything, and column number 7 and column number 8 are identical, right? So basically this identity is valid, so we can vary the variables over the binary values, right? 0 or 1, and we can find out these kind of identities. So we can actually have these kind of laws. Double complement law, complement is same thing as x plus x is equal to x into x equal to x. Idempotent laws, x plus 0 is equal to x into 1 is equal to x. This is identity laws, dominant laws, commutative laws, associative laws. These laws are satisfied and can be proven using the way we have shown. So in fact, I would suggest that you try to prove some of them in your tea time. Okay. So we can define then Boolean algebra is a set B with two binary operations, join and meet, an element 0 and 1, and a unary operation, complement, such that following properties hold. That for every xyz in set B, we have, so this is four tuple system. We have identity law, complement law, associative law, commutative law, distributive law, and so then using these 5 laws we can prove x join x is equal to x and x meet x is equal to x for every x in B. Of course, 0 complement is 1, 1 complement is 0. X join V complement is x complement meet y complement, and x meet y complement is x complement join y complement. Then one can find Boolean expressions for Boolean functions, fx, y, z and gx, y, z. So if table is given like this, suppose, and we ask you find the Boolean expression. Okay, so table is given like this. How do we find the Boolean expression? So as you can see that an expression for f has a value 1 only here actually, right? When x is 1 and y is and z is 1, right? When x is 1 and z is 1 and y is equal to 0, then only f has 1 here, right? So that means we can write down x y complement z is equal to 1 if and only if, so we know that this quantity is 1 if and only if x is equal to y complement is equal to z is equal to 1, right? That means same thing as x is equal to x and z is equal to 1 and y is equal to 0. If x is equal to 1, z is equal to 1 and y is equal to 0 is same thing as x is equal to 1, z is equal to 1 and y complement is 1, which is same thing as x, y bar, z is equal to 1, right? So that means the value of x, y, z is x times y bar z. From this Boolean expression, from this Boolean table, we can actually find out the Boolean expression. Okay, this is how. Now, if you look at for G, we have 1 at this and this place, right? So when we have 1 at this place, means x is 1, y is 1, and z is 0. And otherwise is when y is 1 and x and z is 0. So expression for G is 1 when x is equal to 1, y is equal to 1, and z is equal to 0, or when x is equal to 0, z is equal to 0, and y is equal to 1. So that means x, y bar, z is equal to 1 if and only if x is equal to 1, y is equal to 1, and z is equal to 0. And x bar, y, z bar is 1 if and only if x is equal to 0, z is equal to 0, and y is equal to 1. So these things can be captured into this expression, right? So gx, y, z will be sum of these two quantities because there are two places it is 1. X, y, z bar plus x bar, y, z bar. So therefore, we got the expression for G. So now we know that G is 1 if and only if x is equal to y is equal to 1 and z is equal to 0, or x is equal to z is equal to 0 and y is equal to 1. So from these tables, we can find out the Boolean expression like this actually. Okay. So, okay, a Boolean variable, a literal in a Boolean variable or its complement is known as literal. And many term, I think that's okay. I think we can leave that portion. We can simplify. So, if, for example, if x plus y z bar is there, so we can simplify as x z bar plus y z bar by distributive law, identity law. You apply identity law, then unit property, distributive law, and finally you get this kind of expression. This kind of simplification is possible in the Boolean expression. So I think I leave it here as an exercise for you to check a few of these facts, verify these things by doing some calculations. So if you have any questions, please do ask me. Otherwise, we can close for today's session. And in the next class, we are going to look at this rule of inference and this normalization law. Okay.